Hi everyone, I will come to the presentation of this video on self-excited generators. If you've been following a series of this documentation, you realize that we've discussed a number of self-excited generators. So we said self-excited generators, we've got series generators as well as shunt generators. In the previous lecture, we did a series generator. This time around, we're going to look at the shunt generator. And then in some lectures to come, we're going to look at compound, where we'll discuss two of them. We're going to look at the short shunt as well as the long shunt. So this presentation is about the shunt generator. This, okay. So shunt generators, these are generators whose winding is connected in parallel with the armature. And then one of their principles is that the shunt winding are made of many turns which have got small wire. Shunt means parallel actually. So in here, shunt generators, these are parallel generators. And the circuit looks like this. So you have the armature like that, and then you have the shunt winding, which is connected in parallel to the armature, hence the name shunt winding. And of course, there's a load connected there, having the load resistor like that. So in generation there, you're going to have the current, which we're calling armature current. Once it reaches that node, it will split. There will be a current which will go to the shunt resistor, which we are calling the shunt current, and there will be a current which will be going to the load, which we are calling the load current. Then from here, we can derive some equations. So you've seen that IA, or armature current, is basically the summation of the current going to the shunt and current going to the load. Then we've got the generated voltage. Generated voltage is basically the summation of voltages in the circuit. And I said when you're dealing with generated voltage, you get rid of the shunt winding. So imagine there is no shunt winding there. Your circuit will just remain the armature and the load like that. So if you have that, calculating the voltage drop in there, generated voltage will be the terminal voltage, which is this one, and the voltage generated in the armature, which is that one. So every time you're looking at generated voltage for these circuits, just get rid of the shunt winding and then analyze the circuit like that. You're going to produce this. Then we've got the terminal voltage. When you're dealing with the terminal voltage, get rid of the armature. So if you get rid of the armature, your circuit will remain like that, the one outside there, and you realize that you've got two voltages in parallel. You've got the voltage at the load, which is parallel to the voltage in the shunt winding. So this voltage and that voltage are supposed to be the same, and hence you derive that equation. Then you've got the power output. Power output is the power measured on the load. So it's basically the product of the voltage on the load, voltage at the load, and the current passing through the load, which is that one. So this will give us our power output. Of course, we've got the generated power. Generated power is the power in the armature. So here you've got the generated voltage, which is EG. You multiply that with the current passing through the armature, which is this one. You multiply those, and then you're going to have the generated power. So basically, these are the formulas we can derive from the shunt circuit, which is this one. Let's look at some examples in the next slide. Okay, so we have an example here. It reads a shunt generator supplies a 20 kilowatts load at 200 volts through cable of resistance 100 milliohms. If the field resistance is 50 ohm and the armature resistance is 40 milliohm, determine the following: A, the terminal voltage; B, the EMF generated in the armature. So our solutions there. This is the machine we are looking at. We are looking at a shunt machine. It's a shunt machine because we've got the shunt winding connected in parallel to the armature winding, and of course a load disconnected, right, like that. So from here we can derive the given equations like we did on the previous slide. But before that, we need to take note of what we've been given. So we've been given the following. We've been given the power going to the load, which is that terminal voltage, or the voltage there, which is 200 volts. They've given us the resistance, the drop in the cable, which is 100 milliohms, the shunt resistor, the resistor here on the shunt, which is 50. They've also given us the armature resistance there, which is 40 milliohms. So from here, you can easily find the load current, which is basically from the power at the load. We know that the power at the load is basically the current going to the load times the voltage there. So the power going to the load is 20,000 watts because it's 20 kilowatts, this one here. Divide by the terminal voltage, which is 200 volts. We divide that, we are getting 100 amps. So 100 amps is that one there. For us to find the terminal voltage, the drop in the drop in the cable to the load is basically given by this voltage is equal to IR, I, which is the current, 100 amps, times the resistance. The resistance is the resistor of the cable, which is 100 milliohms. This one here. 100 milliohms is 100 times 10 to the power negative 3. When you do your multiplication there, you're having 10 volts as your product. Hence, the terminal voltage now will be that 200 which was given there plus the drop. Therefore, the total terminal voltage will be 210 volts. Armature current is basically the summation of the current going to the load and the current going to the shunt, which is this one here. But we don't have the shunt current, so we have derived the shunt current. I said when you're dealing with a terminal voltage, you basically remove the armature and you realize that the voltage at the terminals is parallel to the voltage at the shunt. And from there, if you make the shunt current the subject, you're going to have this as your formula. Shunt current is terminal voltage divided by the shunt resist. Terminal voltage is the one we've calculated, which is 210 volts, divided by 50, which is the shunt resistor. You're getting 4.2 amps as the shunt current. Since you have the shunt current, it's easy to find the armature current, which is basically a summation of shunt and the load, which is this one. When you add those, you're getting 104.2 amps as the armature current. Since we have this, it's easy now to find the generated EMF. Generated EMF is voltage plus armature current and armature resistance. Just need to substitute here because we have everything. Terminal voltage we have is 210. Armature current we have is that. Armature resistance is that one. Plug those into your calculator. You're going to get that as your generated voltage. So this marks the end of my presentation on a shunt generator. The next presentation, I'm going to discuss compound generators, and we'll start with a short shunt. Thanks for watching.